Hello Advanced Physics students, this is Dr. Berenzi, and this is lesson 8.1.3. In this lesson we're going to be learning about a new concept called an electric field. And in this lesson we're going to be able to define what an electric field is and its relationship to electric force. In addition to that, we're going to be able to sketch the electric field of one or more point charges. So let's start off by saying, suppose you have a charged body, like this blue object over here. You don't know what its charge is, but you want to study it. And let's say, you probably ask yourself, well, what would be the force on a small test charge if I put the charge here? And then you would put the little test charge there, and you would measure the force, and you'd say, okay, well, that's at one place, but what about another place? So you'd pick another spot, like here. And then you'd pick a third spot, like here. And you'd keep on asking yourself, okay, what is the force on this small little test charge that is caused by our big blue object right here? Well, that's kind of the idea behind an electric field. It's somebody constantly asking this question, and if you were to do this enough times, you would actually come up with almost like a map. So you might come up with a map that looks like one of these two things. So if our big blue object was a positive test charge, then as you place the little test charge around the circle, or in different spots, you would see or observe that the force on that little test charge is pointing away from the charge that we're interested in. And you could do that in all of space, and you would find that you could make a map, and these maps would have the map would have these arrows like this, and you would notice that for a positive charge, all these arrows would be pointing away. And if our blue object was a negative charge, then all of these arrows would point toward the charge. So if we were to keep on asking ourselves that question, eventually we'd come up with a map, and that map is what's called an electric field. Now, if we were studying this big blue object, we wouldn't really care about how charged our little positive test charge is. So what we would want to do is we'd want to actually calculate the force per unit charge. Okay, so we know that the force of our object, let's say it has a charge Q1, it would have a force equal to K, which is Coulomb's constant, times Q1 times our test charge, all of that divided by R squared. But we really don't care about what this test charge really was. So the best way to do that is to calculate actually what is the force per unit test charge. So we would divide by the test charge, and if we do that over here, then we have to do it over on this side, and what you'll discover is you'll see that this test charge divides out with this test charge right here. And you will end up with what's called the strength of the electric field, which in physics we use as E. So the electric field E is equal to Coulomb's constant times our charge that we're interested in divided by R squared. So let's go through a few examples here and learn more about how these electric fields work. So I already showed you this map earlier, a positively charged point that say has a charge Q1, and we know that its electric field, which is force per unit test charge, is equal to K times Q1 over R squared. And I already showed you that first rule of electric fields is that the field lines show the direction of force on a positive test charge. And that is extremely important. We always are considering a positive test charge. Which means if you have a positive charge that you're interested in, all of your electric field lines are going to point away. Oops, went too far. On the other hand, let's think about a negative charge that we're interested in. So let's say that this has a negative charge of Q1. Now you see that all of the field lines are pointing toward that charge. And the strength of the electric field is equal to K times negative Q1 divided by R squared. Now as R squared gets smaller and smaller, what happens to this electric field? Well, the electric field gets larger and larger. So can we see this idea represented on our map? That is, we get closer to the charge, our electric field gets stronger. Well, it turns out that the answer is yes. If you'll notice, closer to the charge, there is just a small amount of space between field lines, electric field lines. So if you were looking at an electric map and you wanted to know where is the electric field strong, you would look for places where the electric field lines are closely packed together. If you wanted to look for places where the electric field is weak, which means the force per unit charge is weak, then you might go way out here where you can imagine that the distance between field lines would be from here all the way down to over here. So that is a large distance to cover, which means that our electric field has become a lot weaker. So the second couple of rules I want you to remember for electric fields is that when you have close lines, you have a strong force, or a strong electric field. When you have spaced out lines, you have a weak force, or a weak electric field. Now you might be saying to yourself, Dr. Brenzy, this doesn't seem very interesting at all. Well, that's because I've shown you the very simplest examples. But things can get very interesting when we decide to start adding multiple charges, and those are the things that are going to cause us to think the most, but they're also the most fun to practice. So let's look at an example of two equal but opposite charges that are separated by a certain distance. So here's our positive charge, and here's our negative charge. Now, what you'll see is that these electric field lines develop a really interesting pattern. Like these ones out here, they look pretty normal. They look like they did before. These ones on this side as well. But you'll notice that the electric field lines that were supposed to be going out in this direction and in this direction, they have changed. This electric field line no longer goes straight out that way. It actually bends and it goes over here to this negative charge. The line that was here directly goes from the positive to the negative charge, but the field lines around it, they also do this little bendy thing, and they actually bend from the positive to the negative charge. You'll also notice that, first of all, field lines never cross. There are no places where these field lines actually cross one another. Now, if you think about what these field lines represent, they represent the direction of a force. Well, if you had two field lines that cross, you are saying that you have two different directions for a force, and that's absolutely nonsense. So, of course, if you think about it that way, it obviously makes sense that field lines would never cross. So, if you're drawing these things, never cross your field lines. Okay? Field lines always go from positive to negative charges, right? Because if we have a little positive test charge, it will be repelled from this large positive charge, but then eventually as it goes out here, it's going to start getting attracted to this negative charge, and it will move right down here to the negative charge. And that's exactly what our electric field lines are telling us. It is actually showing us how a small positive test charge would behave. It would move from here over to here. And it would do so along the field lines. Now that's what makes electric fields very, very useful. It actually shows you the direction that a small positive test charge would move. The last thing I want to wrap up with is that electric fields add up just like vectors do. Okay, so if we were to consider, let's say this spot, and if we were to zoom on this spot, we would have a total electric field that goes like this. It moves from left to right. But why is it moving from left to right? Well, the reason it's moving from left to right is because this positive charge has an electric field that is moving away from it in this direction. The negative charge, on the other hand, has an electric field that is pointing in this direction. Now, because electric fields add like vectors do, we can take this electric field plus this electric field to get the total electric field. And when we do that, and we add it like vectors, it turns out that the total electric field vector is going to point from left to right. And that's why these electric field lines end up bending like this. Because what we're doing is we're adding the electric fields of this point charge plus this point charge right here. And just to demonstrate that principle one more time, let's say that we are looking at this little spot and we're figuring out what its electric field is. Well, we would take the electric field of the positive charge. Now, because it's far away from the positive charge, we don't have a very long vector here because its magnitude is going to be small because the electric field is weak. However, the electric field of the negative charge is strong, so we would have a large magnitude pointing toward the negative charge. And so if we add up our two electric fields, we would get a total electric field that goes from the tail to the tip, and that is pointing in this direction. It's almost pointing in the same direction that the negative electric field would. Okay, so those are a few rules about electric fields and how to draw electric fields. Those 5 rules that I showed you, those are important rules to remember, because when we come to class tomorrow, we're going to actually put those to practice. So, I look forward to seeing you in class tomorrow where we can practice drawing electric fields. Have a great evening. Bye.